Thank you for the introduction, Simon. As you said, I'm in California, Santa Barbara at AIM9 Inc. I'll be talking about combining programmable potentials and neural networks for materials problems. Just a little programmatic stuff out of the way. The people engaged in this project were myself, Dr. Alan Avila, Professor Igor Mejic, and Dr. Maria Funabarova from AIM9. The chemistry folks that we tapped for this were Dr. Shintian Fang and Professor Martin Gordon, who's also at Berkeley. And then at CMU, we were working with Professor Ruslan Salakhudinov and a sequence of graduate students that were engaged on various portions of the project as it was ongoing, and then moved on to bigger and better things partway through. So, set the problem stage. So computing and inferring macro-level properties of chemical material systems. Force field methods in molecular dynamic simulations can be used to infer these. However, it often predicts erroneous values due to not being accurate at the quantum level. Ideally, we'd simulate from first principles and scale up, but obviously this is computationally feasible. And even with density functional theory and periodicity assumptions like QM and MM methods, to mitigate this, it's still somewhat infeasible for many systems. So our approach is to construct general models by taking classical molecular dynamics potentials, which capture the long-range interactions, and then combine these with neural networks, which encode the quantum level logic and correct the near-range interactions. So for the outline of this talk, I'll highlight the kind of classical formulations of the programmable potentials that we developed over a series of years, starting with self-assembly of biomolecules and going to combustion chemistry, and then in this current format for materials properties. And then we'll showcase these results on the problem of absorbing hydrocarbons in these zeolite frameworks. So the programmable potentials methodology, as first appeared in Gudrun Thakker's PhD dissertation, it was developed for encoding information in coarse-grained models for self-assembly systems. And then, as I mentioned just now, we extended this in 2016 to the study of combustion chemistry. So the main idea of the methodology is you start with either experimental data or ab initio simulations, and then you have some type of interaction rules. You have maybe known pairwise potentials. These interaction rules are then developed into logic functions, which are then smoothed into these encoding functions, and we take a pointwise product and we get some modified potentials here, and then we can sum them up to get this approximate n-body potential. If you look in the top right up here, this would be the general formulation of the programmable potential. The orange VJK, that's the pairwise potential, and the SJK is the encoding function. The way we build these is, we specify a class of Boolean functions, which we take as indicator functions on this semi-open interval. So this is a proximity function with a cutoff radius of R. Combine these proximity functions to according to the course level logic, and then replace those with the smooth variance. Here's like a toy example here. We have proximity functions between A and B, and then A and C. And then, so for the interaction logic here, right, C is bound to A as long as B is far away, but when B comes close to C, those two bind, and then C and A release. The issue with all this is right here. For simple interactions like this one on the right, it's fairly easy to specify the logic. When we go to any type of realistic system, that's completely intractable. So the idea here, though, is to replace all that manual effort with a neural network. And then this offloads the kind of human-centric effort in finding that interaction logics. And then additionally, another benefit is if we implement these in PyTorch or TensorFlow or some other auto differentiation package, then we can automatically differentiate to actually get the molecular potential, so we can go and do an MD simulation out of that. So kind of the way it is now, we get the positions of our atoms, compute required pairwise distances. You compute these proximity functions, which are the smooth versions of those indicators on 0 to R. And then we feed those into this neural network that learns the reaction logic. And that spits out some type of encoding function here. So the application area is, as I mentioned, adsorption of hydrocarbons in the zeolite framework. Undoped zeolite framework is a lattice of silicon and oxygens. And then we have a hydrocarbon that gets absorbed into this nanopore here. And then these are used in a lot of industrial applications, which I am not an expert on. So I would refer questions to our chemistry teammates who are actually not on call, unfortunately. So the different hydrocarbons we looked at both doped and undoped zeolite. The doped zeolite replace a little bit of the silicon with an aluminum atom, and then which changes the material properties of the zeolite framework. Within just the undoped framework, we looked at methane, ethane, and propane, and then just at methane for the doped zeolite framework. QChem was kind enough to generate some very high fidelity QMM computations. It was interesting. The QM region is actually defined differently than I would assume, just coming from a physical standpoint. I would assume that they are radially based. So if you're looking at the hydrocarbon, all the atoms in the zeolite framework in a certain cutoff radius would be part of the quantum mechanical region. That's not actually how they define it. In these cases, they define a connectivity base, where they look at the closest silicon atom to the hydrocarbon, then the 4 connected oxygens, and then the 4 connected silicons to those. What's also interesting is in these undoped zeolite frameworks, just the way it's set up, there's actually 12 chemically distinguishable silicon atoms, which we call symmetry lead regions, labeled T1 to T12. And we generated data sets for each of these symmetry regions. Here, red is oxygen, off-white is silicon, and these magenta surfaces here, those are actually composed of little spheres, and each sphere was the center point of the location of the hydrocarbon in the data set. So we computed a bunch of different parameters. The first 4 here were, well, one is the baseline, is pure Lennard-Jones. We use that as a baseline because we know it captures the long-range behavior. 2, 3, and 4, just variations on that where we optimize different parameters. These are all radially based. The ones we want to compare the most are case 5, where this is using the QChem Lennard-Jones parameters and the connectivity-based definition of the QM region. 6 allows actually an additional optimization over the LJ parameters. But 5 and 7 are the closest, and 7 is the connectivity-based definition of the QM region, and then using the encoding functions to determine the logic of the system, whereas cases 1 through 6, this was hand-tuned by Alan. And when we're training, we're actually going to train all on the T1 symmetry and then test on T2 through T12. And I'd also like to highlight that the neural networks we use, they're quite tiny. For a lot of this, like it says here, is 48 layers and 8 nodes per layer. Later on, when we do some transfer tests, we have to actually expand the capacity of the network. And another thing to mention here is we try to learn global encoding functions. So in the previous combustion chemistry project, for each atom, there was an encoding function. So if you had an oxygen-oxygen interaction, there would be an encoding function there. And if there was a third oxygen, right, there would be 2 additional encoding functions there. Here, we get an encoding function for each unique atom pair type. So there is 1 encoding function for every, say, silicon and oxygen interaction, or silicon and hydrogen interaction. And then the metric we compute is just going to be a mean relative error scaled by the range of the energy. So here is just a comparison. of methane in undoped zeolite. This is just on the training set, and as I said, case 5 and case this is 7 are more directly comparable. So it does well on the training set. Case 6 obviously beats it because we have that extra degree of freedom on the optimization. Same way, case 7, the automatic learning of the logic does better than the hand-tuned logic. And here, this is, testing outside the training set. So this is, these are actually the, we compute the mean relative error on each of the symmetries, T2 through T12, and then average them, and that's how we get these errors here. So it works well for methane. We are not entirely sure what was happening here. There is some kind of weird symmetries and very different energies in those symmetries for the methane case. So that might be screwing up things here. So we would like to look at things a little bit more granularly if we're going forward with this project. Here, this is a test of generalizing the learned encoding functions, say for CH4, and then using those for the encoding functions for C2H6. So for CH4, right, we'll learn 4 encoding functions, one between silicon and carbon, silicon and hydrogen, oxygen carbon, oxygen hydrogen, and then we use those to build the encoding functions for the C2H6 in the undoped zeolite. And again, they're all trained on the T1 symmetry for the methane data set. Blue here is the baseline Lennard-Jones. Orange here is the performance where we just use the already trained CH4 encoding functions to construct the C2H6 energy function. It does better than baseline, which is good. Green here is we have a slight amount of retraining. So we take the trained encoding functions on CH4, we construct the model for C2H6, and then we train for an additional, say, 50 epochs. And it drops down quite substantially. And then red is the encoding functions trained directly on the C2H6 data. The ones trained directly on C2H6, beat it on the actual training set, which is T1. But in most other cases, the already learned CH4 encoding functions plus a little bit of retraining actually beats the ones trained directly on the more complicated C2H6 data set. Same story with C3H8. We take the CH4 encoding functions and transfer them to C3H8. Again, the colors are the same. Orange is without retraining or adapting the CH4. Green is with an additional, say, 50 epochs of training. And then red is just the ones trained directly on C3H8. And same story here, except for a few different places. At least they're comparable on most of the symmetry regions. The final thing we want to look at is generalization of CH4 from the undoped zeolite to CH4 to the doped zeolite. And unfortunately, the project ended before we got the full comparison going here. But again, blue is, excuse me, blue is the baseline.
1 more minute of speaking time.
Okay, I think this is my second slide. Blue is Lennard-Jones. Again, this is orange is, just using CH4 from the undoped and constructing the CH4 doped model. And then the green is with a little bit of retraining. So, just to conclude slightly, we have presented Programmable Potentials methodology in the context of adsorption of hydrocarbons in zeolite frameworks. We built a generative model using a structured form that has parametric Lennard-Jones potentials, which correctly capture the long-range interaction of the system, and the encoding functions which multiplicatively modify the LJ potentials, correct the near-term behavior. The generative model, general form allows good generalization of the training data sets. And we can also generalize from simpler hydrocarbons to more complex ones. What I didn't mention in those slides is that instead of the small, 4-layer, 8 neurons per layer, or 8 layers with 8 neurons per layer, we had to go to a slightly higher capacity network, which was like a 1632, 64, 3216, to actually allow the generalization. While the small networks did well, and they didn't generalize to the more complex hydrocarbons unless we can increase the capacity of the network. Same kind of story, we were able to generalize from the undoped zeolite framework to the doped zeolite framework. And thank you for your time.